All right, hi. We're going to look at some of the kind of basic features of R for exploring data. So, first off, we should say that when you have data refers just generally to information. Um, we will, for the purposes of this demonstration, we'll be classifying data as uh, numerical data and categorical data. Numerical data is number data, so like just numbers, measurements or counts of things, um, and and categorical data would be data that categorizes things into various categories. Word data, essentially, descriptive data, but not numerical, not numbers. Um, to start things out, I'm going to I've loaded I'm going to open a data set, which is a Sockeye female monkey body mass. So, okay, so I'm going to load this Sockeye female body mass CSV. So I've navigated to where it is. I'm going to uh, set this as my working directory, and I'm going to uh, read CSV this file 02E1 C Sockeye female body mass.csv. Okay. So let's just I'm going to just type in Sockeye and we'll see what this data set looks like. So it looks like we have 228 rows of numbers, and these are all measurements of mass. Okay, so clearly this is a lot to take in. We want to summarize these numbers. There's a number. One thing I'm also going to do, which is handy if you're going to be dealing with just one data frame, is to attach it. Attach, then you do parentheses, Sockeye, the name of the data frame. So it gave me some issue because the word mass has some other meaning, but it doesn't matter. I can access the variable mass just by typing in mass. Otherwise, I would have to type in Sockeye $mass, which still works. You can see it has all of them, but since I don't want to have to type in Sockeye $ every single time I access this variable, I'm just going to attach the data frame. When I'm done with it, I can say detach Sockeye. So let's explore some of the statistics that are useful for summarizing this data. The first one we're going to look at is probably the some of the simplest ones are probably measures of where is the middle of the data. We call them measures of central tendency. The most common one that you probably are already familiar with is the mean. If I type in mean, Sockeye, oops, my mistake, mean mass. The mean mass 2.028. That's to say that the average mass of Sockeye monkeys is 2.028 from this data. The average, which is calculated by, you just take all the number, add it all together, sum of mass divided by length, the number of monkeys. It's you add it all together and then you divide it by how many there were. Another one would be the median. Median is the 50th percentile. So if the median of this data set is 1.88. So if I was to sort the mass in order from smallest to largest, if I sort it and I just look for the length of mass divided by 2, that index of like right in the middle, I should get roughly the same thing. Now it's not going. Now you can see it's not exact. I'm getting 1.85 and not 1.855, but that's because this data looks like it's got an even number, and so when I divide that in half, I'm not getting the right index. It's probably coming to be it's like one of those two. But anyway, the point is, it's the median is the number that's right in the middle. So for this data set, it looks like these numbers are equally in the middle, so it averages the two of those, 1.855. That's how the median is calculated. So it's the halfway point in the data. For the mean is sensitive to extreme values on the right and the left. So if I wanted to calculate the mean, this concept, a trimmed mean, where I leave off, say, the highest, the 5 on the high end and the low end, I can say trim equals 5. And it's going to be, actually, when I trim off the low 5, these 5 values at the bottom, and I trim off these 5 on the top, these extreme values, the trimmed mean is exactly the same as the median. So there is some asymmetry, and that affects the mean calculation. But if I trim off those extreme values, then the data is a lot more symmetric. So let's see. Some other measures of center is important to kind of know where is the middle of your data. Another concept that's important is knowing how far does the data spread away from that middle. One measure that's simple is the range of the data. To calculate the range in R, if I type in range of mass, what I get actually is two numbers. I actually get the minimum, which if I can get by itself. The minimum of mass is 1.18, that's the lowest value, and the max, which is 3.53. So the range function gives you both the minimum and the maximum. If I want to get the difference between those two, which traditionally in statistics, the range is the difference between the maximum and the minimum, you can do the diff function, and then the range, and then the vector that we're interested in, 2.35, which is to say, that's how far away the minimum is from the maximum. So the range is one measure of kind of spread, how far this thing spreads. Another one that we often use is the interquartile range, which is a way of finding the difference between what's called the 25th percentile, and the 75th percentile. So this is a way I can actually get those two percentiles using the quantile function. I can get the 25th percentile and the 75th percentile, and now these should be approximately the same as the IQR. If I did the diff function of this, it might be off by a tiny bit, but it should be. Oh no, it's the same thing. So the difference between the 75th percentile and the 25th percentile. And when I say 25th and 75th percentile, let's just scroll back up and you can see what I mean. So if you were to take these numbers and chop it up into quarters, so we already decided that the middle is right here between those two. So then the 25th percentile would be roughly it was 1.64. So it's somewhere around here, I think that might be it. And then this is the 50th percentile, and then this is it 2.03? Is that 2.26? Oh, it's right down here. Yeah, so that would be the cutoff for the lower 75%. So they call it the 75th percentile. So percentiles are going to be useful statistics from data. And then the interquartile range is how far away the 25th percentile and the 75th percentile are. So those are called the first and the third quartiles. You can actually get a nice little summary called the 5-number summary, 5num, and that's going to give you 5 numbers. The minimum, the 25th percentile, the median, the 75th percentile, and then the maximum. So those 5 numbers are very much tied in with a plot we'll look at in a bit called a box plot. Now these are all the interquartile range and the range. Well, the interquartile range in particular is known as a robust statistic. Same with the median. They aren't going to be sensitive to the extreme values on the left or the right. As long as your data isn't severely skewed, which is to say severely asymmetric, we tend to use the standard deviation as a measure of spread. Now, standard deviation is, it comes out to be 0.5391. So the standard deviation is, very roughly speaking, it's close to like the average deviation from the mean. Remember, we always said the mean was what was the mean? Was 2.02. So on average, these numbers in this data set are about 0.539 away from that mean. Now, it's not always, I mean, some are closer, some are further away. Now, I should say, it's not strictly speaking true what I just said. Technically, the standard deviation is the square root of the average squared distance from the mean. Which is to say, if I took mass minus the mean of mass, and I squared that, and I divided that by the length of mass, that would give me the average squared distance from the mean. Oops. That is not what I wanted. Oh, I wanted to sum this thing. I need to sum those things up, sum the squared distances, and then I'm going to get a single number. This is actually pretty close to a number called the variance. And actually, for the sample variance, it would be you divide it by 1 less than the sample size, 1 less than the length. So I'm going to put a -1 there. But actually, that's encoded in a function called the variance. See, the variance is the average squared distance from the mean for my data. So you add up all the squared distances, divide by not the sample size, but the sample size -1, and then you'll get the variance. However, the variance is a statistic that is in the squared units. So since this mass was in kilograms, the variance is in squared kilograms, which actually isn't meaningful. It can't be easily interpreted. So the square root of the variance of mass is what's useful. If you find the variance, you square root it and you get another number. That's going to be in kilograms. And that's exactly what the standard deviation is. That's the standard deviation. But like I said, roughly speaking, you could think of standard deviation as an average squared distance from the mean. Now these are the, I guess these are the main kind of statistics that are useful for summarizing, but usually actually a picture is worth 1,000 words. Unless you have a picture of 1,000 words, in which case that's worth 1,000,000 words. So one kind of plot that's really useful is a box plot. I'm going to look at the box plot of mass, and I'm not going to do anything funny, anything special with it. And actually, let's make this full. So over here you see a box plot. The anatomy of the box plot is actually related to the 5-number summary. So what you have, first off, you have this box, and the box has, at the low end, it has the first quartile. The high end, you've got the 75th, the third quartile, or the 75th percentile, and then this black line for the median. So that's what the rectangle is. And then you have these things called whiskers that go down to the low end, either to the minimum value or to what's called the lowest non-outlier. And then you have you go up to the high end, and what we do is we draw this little fence out at the highest non-outlier. And outliers are classified as being no more than 1.5 interquartile ranges from the rectangle box. So you can calculate how wide is that box, add another 50% onto that. That's like 1.5 times that width. And that's as far out as the non-outliers go. Anything beyond that, we draw a little line, and then those little dots are called outliers. Those are just very far away from the rest of the data. That's what an outlier is. It's just some number that's really far from the rest of the data. But you have to draw the line somewhere. And this is the rule of thumb that everyone uses. It's more than 1.5 times the interquartile range, either above the 75th percentile or below the 25th percentile. Okay, now this is the first time I plotted something. We can actually modify this function to have it look a little nicer. Some of the options you can put into a box plot are the main title. I'll call it Sockeye monkey mass. And another one is a label on the x-axis. I'll call it xlab equals group A. Well, there's only one group. And the y label, ylab is the option. I'm going to have it be mass, and I'm going to put in parentheses kg. This is going to be a nice way of labeling the plot, and I'll press enter, and you'll see now we've got this main title. We have a title down below, which actually arguably doesn't do anything for us, and we've got the label on the side. Now, I actually prefer horizontal box plots to vertical, and that can be done very easily in R. You can just go to the options and actually to box plot, and you can specify, add another option. You can say horizontal equals true. But when you do that, the x and the y are going to be switched. So I'm going to change my xlab to ylab and my ylab to xlab. Oops. Oh, horizontal equals true. Why didn't it make it horizontal? Oh, because I didn't spell horizontal correctly. Horizontal. Okay. So you can see what it does. Now it draws the box plot horizontally instead of vertically. And I like horizontal box plots better because we're used to seeing the number line horizontally. And if we're looking at this, you can see the skew is apparent from this, and it is clear that a trimmed mean is going to take care of some of the asymmetry, because you do have what looks like about 6 outliers, which is why the trimmed mean and the median were the exact same thing. A histogram gives you a very, very simple picture of the shape of your data. A more detailed picture of the shape is going to be seen in a histogram. So if I type in hist, actually, you know what I'm going to do? I'm going to keep some of these options. I'm just pressing the up button. Let's see, up. Okay, I'm going to change the function call from boxplot to hist. I'm going to change ylab to be nothing. I don't need to have anything there. For xlab, I'll have the mass, and I'm going to take off the horizontal option because histograms are always horizontal. Anyway, this HIST creates a histogram, and this is what a histogram looks like. It gives you it gives you a bar counting how many observations or how many numbers from our long list of numbers are within each kind of bin. Now here the bins it's not exactly clear, but you can see that like between 1.0 and 2.0 there are 5. So it looks like it's probably going to be between 1 and 1.2, between 1.2 and 1.4, between 1.4 and 1.6, and so on and so on. And so then the height of each bar represents how many. So you can see there's this, you kind of have like two categories, it looks like. You've got like you've got this monkey population, and then that looks like it ranges between 1 and 2.5 or so. That has this mode in the middle, a mode being like a peak, a mountain peak kind of. It bumps up in the middle. But then you've got another population which are like really large sockeye monkeys, and it seems like there's the second mode around 3 kilograms. Maybe there's something genetically or biologically different between like two subpopulations, and that's why you see this second mode in the distribution. It's curious, and there's probably a reason for that. This kind of thing this is the kind of plot that will make these features of the data visible. When I show you an option you can add, you can specify how many breaks you want in your data, and you can see, and actually when you say breaks, it's actually the number of bars. If I had said that the breaks equal 3, what I'm going to get is a very, very coarse look at the data, and it really hides all of these features. So if you have too few breaks, it doesn't look good. If you set it too high, I'm going to put 100, and you'll see if you put it as too high of a number, it becomes very spiky and jagged. So usually the number that's automatically picked is going to be good. If you want to play with it a little bit, you can play with the numbers, but oftentimes the default number is pretty good. Sometimes the default number isn't good because R is just using an algorithm to try to calculate the optimal number of bars, but it could very well be wrong. So there's a few other kinds of plots that are good to know about. One is a stem and leaf plot. It's stem is the function, mass. If I type stem mass, what I get is actually not going to show up as a plot, but it's going to show up in my console output. And what it has, you can see what it actually is doing. It seems like it's actually flipping the histogram 90 degrees to the right, clockwise. But what you have here, in fact, is it's actually a chart or a form of a table, I suppose you could say, where you actually have all of the original numbers. So it says here the decimal point is 1 digit to the left of the vertical line. So what you have on the left, you've got these things called stems, and for the first stem, it's 11. So 1.1 something. So all of the numbers in our data that started with 1.1 are going to be listed in increasing order. So we had a 1.18, and that's what this first number is. We also had 1.20 and a 1.22 and a 1.25. We also had 1.31 and 1.35 and 1.38, 1.39, and so on. So you can see it actually is giving you not only the shape, but it also actually is giving you all of the original data as well, in case you wanted to look at it. You can specify an option for the stem and leaf plot called scale. If the plot is too big, you can say scale equals 0.5. It'll make it half as big. So this is going to collapse it into half as many rows, and so, but you still get this shape. You have this one big mode, and you have this second smaller mode around 28 or 2.8 kilograms. So you can see the first mode is at about around 1.6 kilograms. The second mode's around 2.8 kilograms. That kind of, the stem and leaf plot is nice because it makes these a little bit more precise, these features of the data. You can give it a numerical value right away. A couple others, we got a strip chart, which it puts all of the data, represents all the data as little dots or blocks in a line. So I'll Sockeye monkey mass, and I'll give it the xlab the same as the histogram of mass in kilograms. So this is what a strip chart is going to look like. Oops, I didn't type in xlab. I put an extra L there. Let's try that. What was I saying? Okay, so this is what a strip chart's going to look like. And as you're probably saying right away, this is not very useful because there's so much overlap. And if there's a lot of overlap in your strip chart, you can add a little bit of variation. You can say method equals quote, double quote, jitter, jitter. It's going to give it a little bit of variation, and when you put it like this, it actually makes it a little bit more clear that you've got two. It really looks like two populations, one centered around, as I said, like about 2.8 or 2.9 kilograms, and one centered around 1. It looks like it's centered around 1.7 or so. You can play with other features to make the strip chart look nicer. For one thing, you can change the shape of the points that are plotted, and that's using this PCH option. That's the point character. If I say PCH equals 16, I'm going to get circles, and of course they're all black now. I am getting a lot of overlap, with the problem with the overlap again. So what I'm going to do is I'm going to make them semi-transparent. I'm going to say COL is the color. I'm going to use a function RGB to create a color that's going to be just gray, 0, 0, 0. Although I could make it blue if I wanted to. Let's make it blue. I'm going to RGB. I'm going to make it blue, and I'm going to make it 0.15. That's how opaque I want them to be. 15% opaque. Each of these, the red intensity, the green intensity, and the blue intensity, take a value between 0 and 1. So what I should get now is I'll see the overlaps a little more clear. So that's kind of pretty. So where they overlap, it gets darker. You can play with strip charts in different ways. You can change the character. Now there's another method you can use on a strip chart that changes it to what's called a dot plot. Actually, I'm going to go back. I'm actually going to keep PCH at 16 to make little black circles. But what I'm going to change is the method. I'm going to use stack, and there's actually another option I want to add. At equals 0.15. So we'll see. This is actually going to lower these to be down at the bottom of the plot. And what we get is actually the same kind of shape we saw in the histogram, where these dots are just stacked. Although there still is a lot of ugly overlap. There's some things you can do to affect that. Actually, I think is there an offset feature? I'm going to actually, what I'm going to do is I'm going to put the same data into a strip chart, but I'm going to round the data to the nearest 1 decimal place. And when I do that, it's going to round, so we're not going to have it's not going to be 1.27, it'll be just rounded to 1.3. If I round them, what I get is these stacks of dots that are going to a little bit more clearly show, again, the shape of the data. Although you could probably say to yourself, why go through all this trouble? You could just make a histogram. And I'll say touche. Okay, now there's one kind of plot that's actually really nice called a density plot. And we'll be learning about probability distributions in subsequent chapter, but the idea of a density plot is it attempts to take the sample data and estimate from it what the population it came from looks like. The population is going to be so large that you could actually plot a smooth curve that goes that traces the shape of the population data, and so I'm going to use plot instead of I'm using the plot function to make a density plot. Plot density of mass. I'm going to put the main as Sockeye monkey mass, and again x lab equals mass in kilograms. So this is what a density plot looks like. Oops, I made a typo. Let's see, plot density. Oh, I put in an extra parenthesis. Okay, here we go. So this is a density plot, and so this it's estimating, so it's smoothing things out quite a bit, and it also you can fiddle with some of the options. I'm not going to do that now, but you can fiddle with some of the options. But the idea is that it attempts to estimate what the underlying probability distribution might be that would generate the data that you got. And that'll make more sense next week. But if you just want to see the shape of the data, a density plot is kind of nice. There's other plots that are trendy, like a violin plot. And there's libraries in R that makes violin plots. Violin plot is essentially you take a density plot and then you take another density plot. You do a mirror image of it, and what you get is like kind of a this one would look like it would curve up down. Anyway, I'm not going to make a violin plot for this. Okay, so these are a whole lot of kinds of plots that you can use to just get a picture of numerical data. So far, it's just been univariate numerical data. What we're going to look at now is univariate categorical data. So I'm going to open another data set. Actually, let's clear this. Okay. And okay, so I'm going to get a different data set in called cloudy read.csv, cloudy.csv. So what we have in this data set, just to look at it, we have a whole bunch of days from the month and what the weather was, partly cloudy, clear, or cloudy. So if we wanted to summarize this, the most obvious way to do it, well, one way to do it would be to create a table. I'm going to actually attach cloudy. And so if I create a table of cloudy, what it's going to do is it's going to, cloudy, the variable that I want is weather. I'm sorry about that. So the variable is weather. That's what I want to be dealing with this whole time, weather, the weather variable. And the table summarizes it very nicely, numerically. If you want to summarize it visually, a bar plot is a great plot to use. I'm going to do a bar plot of the table data. And that's going to, without any other options, it'll create basically what I want. What I've got here is this, I'm plotting a height for each of the bars. Now I can add in some other features. I can add main equals Central Park weather. I can add Y lab equals frequency, which is what it is. It's counting the number of days that it was each weather type. And then I can add X lab equals what the weather was. So you can add the labels to a bar plot the same way you add it to other kinds of plots. If you wanted to get the relative frequency instead, what you can do is just divide your table data by the either the length of the weather variable. Oops. But I should change this. This is not frequency anymore. This is, I can say proportion. This is what proportion of the time it was clear, cloudy, or partly cloudy. You can see the proportion of the time. It's like 35%, a little bit more than 35%, or like 29-ish%, so forth. In fact, if I just did my table, if I just typed in table of weather divided by the length, I would get a proportion table, right? Those are the numbers that are being used to generate this bar plot. Okay. I mean, that's probably, I mean, if you want to visualize univariate categorical data like this, a bar plot's really what you want to use. There is maybe some other kinds that I don't know. You could use a pie chart um, if you wanted to, but honestly, pie charts there's really very little that a pie chart does better than a bar chart. If you have more than two categories, go with a bar chart. A pie chart is just it's hard for the eye to judge angle, and when there's more than two categories, it's really hard to decide. I mean, it would be so hard to decide which of the three slices was bigger. So, okay, so far we've looked at univariate data. We're going to look now at bivariate data, where we have two variables. I have another data set that I'm going to load up, which is the lengths and weights of African snails, Achatina fulicas. So Acha, I'm going to read .csv. It's Achatina fulica .csv. If I spelled it right, I have to put the quotes in, and we should good. It loaded up nicely. So what I've got, I'm going to look at the head of this of this. You'll see I've got IDs, I have weights, and I have lengths. So if I wanted to see how does weight and length relate to each other, I can plot. I'm gonna attach Acha just for ease of notation. So I'm going to plot. The first variable is going to be LT, and then the second one is going to be WT. What I get now, you can see the length is going to be the horizontal variable and the weight is the vertical variable. But if I want to, again, I want to make it look a little nicer, I'm going to change the main title to be Achatina fulica, measurements, and I'll have the Y lab be weight in grams and X lab length in centimeters. Yeah, and I get a pretty nice scatter plot. Now, again, there's a lot of overlap. If I wanted to play with this, I can do what I did before. PCH equals 16, and I can say the color equals, let's do RGB, let's do 000, comma, 0.5. That's going to make them gray solid circles, and they're going to be 50% opaque. We'll see what that looks like. Yeah, I mean, I don't know. That maybe it's a little dark. I'll change it to 0.25, maybe even 0.1. You get a sense what you can see. Making them semi-transparent makes the density of the points really stand out. There's actually some other plots that might address that issue even better, but we don't need to get into them. I think already this is a very pretty plot. Let's see. So now the scatter plots is pretty much your go-to plot for looking at two numerical variables and how they relate. The statistic that measures how well they relate in a straight line is the correlation, COR, of LT, WT. The correlation is a statistical measurement that can measure from -1 to 1 of how strongly these two variables relate to each other in a straight line. So a correlation of 1 means they're perfectly correlated positively, which means as one variable increases, the other one increases. So going from the bottom left to the upper right. A negative correlation means that it tends to slope downwards like that, from the top left to the bottom right. And if the correlation is close to 0, then that means that there's really no relation between the two. I'll make an uncorrelated data. Let's see if I can. I'm going to do another scatter plot, but in my variables are going to be created randomly. I'll just call it uncorrelated data. And I'm going to have my variables be, let's see, R norm, let's do 100, comma, 15, comma, 2, and R norm 100, comma, 9, comma, 5. The 9 and the 5 don't really matter. This is what 100 uncorrelated data points would look like. Let's change it to 1,000 so you can really see a little bit of overlap where there are more points. Okay, this is what uncorrelated, normally distributed data would look like. We haven't even talked about what normally distributed means, but you can see it doesn't. The data points do not fall in a straight line. It just looks like a cloud. That's uncorrelated data. And here would be like, well, that's enough of that. One thing I will point out is there's a measurement of correlation. Actually, it's called the coefficient of determination. It's called otherwise known as R squared. I'll type in RSQ, and that's the correlation of WT and LT. If you square it, RSQ, let's type that in. So 0.860063. So the R squared is it kind of tells you what proportion of the variation in one variable, in this case it would be like the length, it can be explained by the variation in weight. So how much of the variation in one can be explained by the variation in the other. And once we get to linear regression, you'll understand what I'm talking about way better. But for now, I guess correlation, just know it's a measurement of how well the data are on a straight line. Okay, if you have two categorical variables that you want to compare, I'm going to open up another data set. Parasite read.csv. I'm going to clear this actually first. Okay. This is, let's look, what are the files called? Oops. The Parasite data, I think it's just called Parasite brain warp. Parasite brain warp.csv. Oops, I must have typed something in wrong. Warp. Okay, so what we've got in this data set, let's look at the head of Parasite. It looks like you've got two categorical variables, and this is for fish, whether they've been affected by a parasite or not, and what happens to the fish. Do they get eaten or do they not get eaten? So you can either have light, uninfected, or you have light infection, uninfected, and then there's also heavy infection, I think, and whether or not they got eaten at the end of this experiment. Turns out that this parasite makes the fish more likely to get caught, and we'll see that. What I'm going to do is I'm going to show you what's called a contingency table, where we have each of the, so if we have two categories for eaten and three for infection, that means there'll be 6. That's a 2x3 table, and let's see how we make that. So we can, I'm going to actually create this table, parasite table, and I'm going to use the table. I'm going to save this table output. Parasite table, parasite $ infection status, comma, parasite $ eaten. So the two variables are going to be those, and then I'll have DNN equals names parasite. So the DNN is how are the names for the table defined, and it's just going to be the two names for this data frame, infection status and eaten. Now this is not going to create an output. What I have, if I want to look at it, I have to type in parasite table. So what we have is the count. How many were in the high infection status and got eaten or didn't get eaten, and so forth. This is numerical summary of this categorical data is really just frequency. You're just counting the stuff. If I wanted to get row sums, margin.table gets sums parasite table, comma 1 will give me row sums, which means so that's how many were high, light, and uninfected, which actually I would get if I just did a table for parasite infection status. It's the same thing. If I wanted to get column sums, I can ask for a marginal table and put in the option 2. Oops, I should call it column sums. But what might be useful is to add the margins to the table. If you use the function add margins, parasite table, what you get is a table that has a sum column and a sum row. So if you kind of think like you have the row sum for each of these 3 rows, and then you have the column sum for column 1 and column 2, and then you have that final sum, which is 141, which is the sum of the row sums, and it's also the sum of the column sums. That's the total sum of the fish that were in the sample. These so far, if I wanted really some patterns to emerge though, make them really pop out, a proportion contingency table will be really useful. Now it's not so useful to just take the parasite table and divide it by n row of my parasite data. You get proportions, certainly. Those 6 numbers will add up to 1. But what I'd be interested in is looking at if for each row, how does the proportions divide up row by row or column by column? I'll show you what I mean. The prop.table function, parasite table, comma, if I put comma 1, this is going to be a row proportion table. What I get is row by row, every row adds up to 1. So I can see very clearly for those fish that had a high infection status, 80% of them got eaten. If there was a light infection status, only 22% of them got eaten. And for uninfected, 0.02, that's 2% of them were eaten. That makes the effect of infection status very evident. You can look at column proportions as well, if that's the kind of thing that would be useful to look at. You could just have to change that option to 2, and that we're getting. So for those fish that got eaten, 77% of them were in high infection, 20% of them were light infection, and 2% were uninfected. For those that didn't get eaten, you can see that 52%, 53% roughly were uninfected, and so forth. You can sort of think of it in that regard as well. Now, these are long decimals. If you wanted to, one thing it's good to mention, looking at these decimals that go on really long, if you wanted to round it off, you can set that options equals, or options parentheses, it's an options function, quote, digits equals, let's say digits equals, let's see, 2, I'm going to say 2. And so I'm going to do the same row proportion table. So this actually rounds it off to 2 decimal places, which is nice. So I can see now 20%, 78%, and 98%. I'm sorry, this is rows. So it's 20%, 80%, 78%, 22%, so forth. So setting the digits equal to 2 is a good, nice way of just getting R to round for you. And then you can set the digits back to 6 or whatever you wanted it to later on. Let's look at a plot that compares these two categorical variables. A bar plot can be made that's like a side-by-side bar plot. You put in the table data, Parasite table, and even if you don't put anything else in, it's going to be fine. But actually, you can see what we get when I put in the Parasite data. You've got each of the columns created another bar. So let's add a label. The xlab equals eaten, and the main is Parasite brain warp. So this makes it not entirely clear. These stacked bars, the problem is you were probably interested in proportions more. I'll show you a couple different ways you can make these bar plots. So this is a stacked one. If you wanted to do side by side, you can just add one more option, beside equals true. You get a side by side bar plot, but still we're missing a legend that says what the different colors are. You can actually turn that on, say legend.text equals true. That helps clear things up quite a bit. That the infection status is there, and then now you can see really what's going on. The problem is, though, you might just if you have way more fish in the no category than in the yes category, the pattern might not pop out at you. So you might want to kind of standardize the two by looking at proportional like stacked bar charts. So what I'm going to do is actually I'm going to instead of putting the Parasite table in, I'm going to put in the prop table. Prop.table. Put in the column proportional table, and I'm going to turn off beside. And what I get now is something where I can really see how the proportions stack up. No pun intended. You can see for those fish that were not eaten, only a very small proportion of them were highly infected. Most of them were light or uninfected. And for the ones that did get eaten, it's a very different picture. This parasite really has the effect of making these fish easier to catch. My guess is it's some parasite that probably breeds inside the gut of the whatever bird or whatever it is that's catching them, and that's probably part of the life cycle of the parasite. Now, if you have a categorical variable and a numerical variable, you want to see how they relate. What essentially you're doing is you want to look at what the distribution is for the numerical variable categorized on the different kind of categories of the, like, split up by the different categories. I have a data set of heart disease by over 4 different states. So heart disease read.csv, heart disease mortality.csv. Oops, I must have again typed something wrong. Heart diseases, and no, it's just disease. Okay. If we look at the head of actually, let's look at the structure of heart disease. So we've got location, and we've got see AK. Let's do a summary of heart disease. Oh, that doesn't tell us much. Look, I mean, the location is. Let's make a table for heart disease $location. Okay, so this makes it very clear. There were 201 observations in AK, which is Alaska, I'm pretty sure. AL, I think, is Alabama. 752. Then we have Arkansas, and then Arizona. So if we want to look at, say, a box plot, well, one easy way to split up a box plot of heart disease $ data value, we can put in the little tilde and have the factor that we're splitting up by. Heart disease location. And I'm going to say horizontal equals true, and I'll say main equals heart disease by location. Oh, the X label and the Y label are a little bit ugly looking, but what we see here that's what the side-by-side box plots are going to look like. So what we'd have here is a box plot for each of the three, or four, sorry, locations. And so doing something like this can make big patterns pop out. It looks like, oh, it's very obvious that the population is very different. Alabama and Arkansas are very, it seems like, higher numbers than Alaska and Arizona. And now I have to apologize, I don't know the units of this data set, so I'm not going to be able to delve too much further deeper into the meaning of it. But if I wanted to say, if I want to just look at two of them side by side, one thing to do would be I can get heart disease for each of these specific locations. Let's say if I want to do Arizona compared to Arkansas, let's do Arizona and Arkansas. AZHD, I'm going to save in this heart disease. I'm going to get where heart disease $ location equals AZ. What I'm doing here is, and I'm going to get the second column. So this is a way of subsetting my data frame where I only want to get those rows where the location is AZ, and I want to get the second column. So I get, heart disease. I, of course, again, put an S at the end. Okay, so what I have now is my Arizona heart disease data in its own vector. And I'm going to get a Arkansas as well, change it to AR and AR here. So if I wanted to look at just those two side by side, I could create a box plot of, I'm going to repeat the this pretty much. What I'm going to do is I'm just going to take this first part of it, the code I used before, and just have AZHD, ARHD. And in order to label them, I'm going to say names equals Arizona, Arkansas. So the names option specifies the names of the different data sets, how you wanted them labeled in your plot. So this is nice. This makes, if this is a way of comparing just those two, if comparing to box plots isn't your thing, you can do this using, I personally am not so fond of comparing histograms. I think the density plot is a better way of making this pop out. What I'm going to do is I'm going to, if I was to plot the density of AZHD, I'm going to get this density plot. And if I plot the, to add another curve to this, you have to use the lines command, density ARHD. And what I get now is two density plots, and you can really see side by side how different they are. Problem is that they're both lines, and so you need to probably specify the type of line. If, for example, I'm gonna redo the first one, and I'm going to actually specify the main title to be um, density comparing. I'll just say comparing heart disease in Arizona and Arkansas, and then I'm going to add the other line, but I'm going to give it an option called LTY equals 2. LTY is the line type, and the LTY equals 2 will say this line type is going to be a dashed line. And by adding this as a dashed line, it makes it very obvious where it's different from the first one. You can also, if you wanted to, say color equals blue. If I want to make it blue, you can change the color. And so if I wanted to now add a legend to this, there's a legend command. I can say x equals, I'm going to put it up at x equals, let's see, where's the location? I'm going to put 500. I might have to play around to get it in the right place, but you have to specify the location where you want it to be. 0.005. This is probably going to be wrong. Y equals 0.005. Legend equals, I have to combine AZ comma AR, and I'm going to have to specify LTY equals 1 and 2. The two styles for the legend are going to be solid line and dotted line. That's 1 and 2. And then the color of them, I'm going to have black and comma blue. Now this might be in the wrong place, but we'll try it and see. I'll fiddle around and try to fix it if it's wrong. Yeah, it's not showing up, so I'm going to change this to be found. I think that X and Y is the upper left corner. I'm going to set it at 600, and I'm going to set Y to be at 0.004. Let's see. Yeah, that. Oh no, this isn't good. Legend. Oh, you know what? I see exactly what my problem is. I didn't separate these by I had AZ comma AR. I wanted AZ in quotes and then comma AR in quotes. Okay. Now when I make the legend, it should put it in the right place, but it may need to. I have to redo everything. So let's start over with the first plot and plot the main thing. Then I'm going to redo. I'm pressing up a few times to make this blue dotted line, and now I'm going to create my legend again. And that's pretty good. So I added the legend. It's in a good spot. And I've got these three, so these 3 lines of code all added different things to this same plot. So this is one way of looking at two kind of distributions of data and seeing how different they are. If you didn't want the center to be such an issue, one thing you can do is you can either standardize the two data sets. By standardize, I mean you first divide it by the standard deviation. I'm sorry, you first subtract the mean so that the mean becomes 0, and then you divide it by the standard deviation so that it has the same standard deviation. But that way you can see whether you're not looking so much at the how far, like the location and spread of the data isn't such a factor, but really it's just the shape of the distribution. But one way to look at that is using a QQ plot. AR AZ HD comma AR HD. A QQ plot, it plots the quantiles against each other, and what you get is a bunch of points that you can see here. If these points are on a perfect diagonal line, that means that the two distributions have the same shape. If they're not on the same on the diagonals, here where the Arkansas is higher, like it kind of brings it up. So that means that as the Arizona, the Arkansas shape is more, I guess, has more of a more concentration towards the left, because it the as it increases in quantile, like, actually no, that would mean it's skewed to the left. There's a left skew, because as you move in quantiles, you kind of have bigger jumps, and that's what brings it up. I'm not going to get too hung up on this. I just want to show you a few different ways of comparing categorical data. We'll get it. We'll talk about this in class. I think that's probably enough of an overview of just ways of comparing data, like exploring data in R visually and also with summary statistics. Bye.